Okay, so now let's look at the time complexity of our merge sort implementation. So looking at our merge function, what it does is constant operations like comparing and dividing, and then the two recursive function calls, two partitions which are half the size, and the merge function call. So our recurrence relation should look something like this. So twice the function call for half the size, and the merge function for the partitions. So uh, the a detailed analysis on the time complexity of the merge function is here, but from intuition, we should be able to guess that the merge function, since it needs to go over each element to be merged at least once, it will take at least that many times to I mean since it goes through each element at least once, its time complexity should at least be linear. So here you can see that for each element we go through each element and put them on the list, and then put them back there. And then looking at our function here, there are no nested for loops or while loops, so we can expect that the time complexity of our merge operation to be O of n. So knowing that, we can proceed to the recursion tree, wherein for a specific level, we put the running time of the merge function itself without the recursive call, which is just n plus some constant c1. And then for the next level, so the recursive call for this function will be here in this next level, which is t of n over 2. And then, so the time it takes for us to accomplish t of n over 2 is n over 2 plus some constant plus the recursive call, which is at the next level. So you'll notice here that for each level, the sum of n terms always results to 1. Because here we have 2 n over 2 terms, here we have 4 n over 4 terms. So for the 0th level, we have n plus some constant 1, plus the constant. Then for level 1, we have n plus twice the constant runtime. Then for T2, we have n plus 4 times the constant runtime. So we can expect that the coefficient of 4 is actually the power of 2, or 2 raised to the current level of our recursion tree. So we can form a summation for this, which is here. So the summation of n plus 2 to the I times c1 from I is equal to 0 up to k minus 1, because for t equals k, where k is the deepest level, we have n c2 terms. So that is this term right outside here. So doing some using the properties of summation, we can distribute this. So we get nc2 times kn plus c1 times the summation of a geometric series where the common ratio is 2. So that simplifies to 2 to the k minus 1. Now, similar to binary search, we can get k, or the deepest level, when the partition length is approximately 1. So that means k is approximately the log base 2 of n. So substituting this to this equation right here, we get n log n plus c2n plus c times n over 2 minus 1. Why is that n over 2? I think this should just be n minus 1. Okay. So adding them all up together, we get the asymptotic notation. So the big O of t of n is actually n log n, which is definitely better than O of n squared. So n log n, sometimes called log linear, we can say that this is much better than n squared since, well, n is bigger than log n, so n squared should be bigger than n log n. So this is definitive proof that the merge sort time complexity is higher, is better than our n squared sorting algorithms that you may have encountered before.